Welcome to this new lecture. In last lecture, we discuss and study the convolution neural network, but actually we only study the convolutional layer in convolutional neural network. In this lecture, we will also discuss convolution layer, but not convolution layer. Actually, we will discuss its parameter like size, padding and stride. Actually, these are the parameter of convolution layer. So we start. Introduction to convolution neural networks, a gentle overview of CNN, understanding images. It's mean the input of a convolution neural network is an image, and the output of convolution neural network is the label or class of image. For example, this is the image, this is the input image which we feed into the CNN model, and then CNN, and as a result CNN model predict its label. For example, predicted to be a cat, and if we feed this image, then CNN predicted to be a dog. If CNN is a well-trained model. After this, we see or understand some other things. Many things indicate that it was a cat or dog. Actually, its discussion is about two images. So, for example, whiskers, shape, eyes, fur, colors, and etc. Can an algorithm or predictive model do this? Okay, building an intuition for CNN's model. It's mean what digit is this? Okay, how would we program a computer to know this? Actually, these are some questions about CNN models. Overall shape, maybe if something lies in this region only it is one, or but what happen when this one is shift right or move right side? But what if it is shifted? So it's mean in these conditions what is the attitude of CNN models or behavior of models. What if we had filters that could scan all parts of an image? This is an example or a visual example of whole CNN models, and the whole CNN model consists of different layers. But in this lecture, we will discuss its first layer, which is called convolutional layer. Then, in the coming lectures, we will discuss and study and understand all layers of convolution neural network like pooling, fully connected layers and output layers. But in this lecture, we will limit it to convolution layer. So these are the different layers of convolution layer. This is the input layer and this is the output layer, which gives us the probability of this image. For example, cat is 0.91 probability. It's mean CNN tells us this image is 99% chances that this is a cat. No convolution. In a convolution neural network, a convolution layer is responsible for the systematic application of one or more filters to an input. The multiplication of filter to the input image results in a single output, which is called a feature map. We study feature map in this lecture later. The input is typically three-dimensional images: rows, columns, and channels. It's mean an image consists of rows, columns, and channels. And in turn, the filters are also three-dimensional with the same number of channels and fewer rows and columns than the input image. It's mean filter matrix is a small matrix than input image matrix. Now we see what is convolution operation. Mathematical term to describe the process of combining two functions to produce a third function. In our situation, the output called is a feature map. Feature map is the actually result of the convolution operation between input image and a kernel or a filter weights. We use a matrix called a filter or kernel that is applied to our input image. So the first function is the image that is combined with the kernel or filter, which produce a feature map. Example of a convolution operation. For example, or suppose that this is our input image and this is our filter, and then we perform a convolution operation between input image and filter. Actually convolution operation is a dot matrix multiplication, not a tough or complex operation. And this filter is, and when we apply or perform dot multiplication between input image and filter kernel, then we get another matrix which is called output matrix or feature map. This is the method of perform convolution. First, this filter is keep on this area of input image, and then corresponding elements multiplied with one another, and then this result is a 2, and then this result is stored in output or feature maps, and then so on. So we slide this window one step horizontally or one step vertically, but this one step moving is also called stride. So we also discuss stride in the later this lecture. When this filter is moved from start to end, then our feature matrix is complete. Image features. One feature maps are actually feature detectors. Why did we do this? Because convolution filters or kernels detect features in images. Our convolution filter as an edge detector. We can also, our convolutional filter is an edge detector. For example, where pixel values of an image change, then we say this is a edge. For example, this value is 1, this is value is 1, this is one edge, which shows gray, and this is 0. It's mean intensity change from 1 to 0, and then 0, and this is one edge. So when we multiply dot multiply with this input image, we get this feature map, and in this feature map actually extract the edges of this input image. So this is the edge of this input image. These are the different types of convolution filters, and their results after convolution and input image are here. So we see these. This filter is called filter or kernel is called identity. Identity means when we convolve this filter with an image, the image will be remained same or unchanged. Next, this filter is edge detection, and this filter is also edge detection, and this filter is also sharp edge detection. If we sharp the intensity values or colors of images, then this filter is convolved with input image, and then the resulting image is sharp image. If we blur image, then we use this kernel, and if we use for we increase the blurring or blurred image, this is the Gaussian blur filter used to add blur in the image. And this is the filter results, or you can see the intermediate results of different convolution layers. Okay, you are seeing that the input image has a high dimension or a big big dimension, and kernel filter has a small dimension, and then feature matrix is also a small dimension than input image dimension. So this is actually a formula. Feature map size formula is n minus f plus 1 is equal to m mean feature map. What is n? N actually dimension of input image, f mean filter means dimension of filter, and plus 1 is its formula. So when we determine determine the size of feature or dimension of feature before convolution between input image and filter, then we apply this formula where we put dimension of input image and dimension of filter image, and then plus 1 and is equal to 3. You can see this is a 3 by 3 matrix. So this formula is used to calculate the dimension of feature map. Next, feature detectors. How feature detectors help to classify images? Actually, convolution layer extract the all features of an image, and then these features we pass hidden layers, and then hidden layers predict the label of the image, which is, and in this example it extract or predict the label cat 0.99 and dog 0.01 because the probability of cat is high. So we easily see that, or can say that the input image is dog. Input image is cat. Next, how classifiers use feature detectors. Actually convolution filters are feature detectors, which is important feature detectors. For example, this feature contains the these parts. I think these parts of ears, these parts of features, and this filter actually contain the eyes feature, and this contains I think a mouth like features, and then these features feed to the hidden layers, and hidden layers predict the label of on the basis of these features. The hidden layer predict the features of input image. Next, these are some examples of traditional feature extractor methods of computer visions, which are used in computer vision before the invention of convolutional neural network, which are hogs. Hogs mean histogram of gradients. Similarly, shift surf, ORB, and PHOG and HARC is classifier. But now the convolutional neural network is mostly used and well performed than these traditional feature extractor methods. The layers of CNNs. Again, we see the layers of CNNs. CNN consists of following layers: convolution layer, ReLU layer, pooling layers, fully connected or dense layer, and output layers. And in the coming lecture, we we understand and discuss all layers one by one, but in this lecture we are limited to understand convolutional layer. Convolution on color images. When we have a color image, this is actually a convolution between a filter and a grayscale image. Grayscale image single values, but when we have a color image, actually color image has three channels. It means a color image intensity values or pixel values of color image consist of a pixel of one pixel of color image consists of three values. One for RGB, it means it has a color image has RGB format color. It means one value of pixel is red, and red value for red color value, and an other value for green and blue. So in this type or for color images, we need three filters. Each color for one filters. It's mean each one filter required for one color, and the green color for and green filter is required for green part. Similarly, color filter is required for color part, and then we convolve with each other, but we use in two-dimensional, but the feature maps will be two-dimensional. Where feature map is one, because filters are three and input images are three consist of three matrix, but feature matrix is a single matrix. Why? So because when multiply one by one, and then this multiply this value multiplied by this value, and this value multiplied by this value, and then add these three values, so this is 3. So in this way the feature matrix or output matrix of RGB image also a single matrix. Advantage of having a filter for each color. So this is so many explanation. I think you can study easily. Kernel size and depth. We look at some of parameters that define our kernel parameter. So we study some parameters of convolution neural network or convolution filter, which is kernel size, depth, 1 for grayscale, or 3 for RGB color, stride, and padding. So these things, these parameters we see practically in a program. So we see on programs. So now we perform convolution operation on an input image, and then we see what effect of size after convolution operation, what affect the size of input matrix, padding, and stride. We understand these things with this code. Okay, run this cell. In this cell we import two classes from Keras API. First one is sequential and second one is convolution 2D, and third we import as array class or as array function from NumPy library. Next we define an input image and input data in list form, and then we convert this list into NumPy array by using as array function of NumPy, and then we reshape our function in this dimension. It means 1, 8, 8, 1. 1 is the channel, I mean it is a grayscale image. 8 rows and columns. You can also width and height, and 1 is the number of samples. It means fill. It's mean this is the number of samples. So at this time we have only one sample, so 1 is here. And then we run this cell to check the shape of data. So our shape is converted in our required shape. Our data is converted in our required shape. In next cell we create a model by using sequential class, and then we add in this model a convolution 2D convolution layer add, and then we set its parameter filter is equal to 1 and its kernel size equals to 3 by 3, and then we pass input shape is 8, 8, 1. So in input underscore shape there is no need to pass number of data samples, only width, height and channel of our data. This is the syntax of convolution 2D layer. So we add the convolution layer in our model. Now we check the summary of our model. So it's mean this is the actually dimension of feature matrix in the result of this. So you can see that our input image dimension is 8, 8, 1, but after convolution with the kernel matrix of 3 by 3, the shape will be, or dimension will be 6 by 6. It's been decreased by 2. So next we define the values of our kernel matrix or filter matrix, and then we change in numpy array by using as array function, and this is the bias value we have already discussed in previous lecture. Then we set these weights in the model which we have already created in our second cell. Okay, now we apply the convolution operation. Okay, now we check our feature matrix values. These are our feature matrix values, which is column whose dimension is 6 by 6. And next we see the problem of border effects. I hope you study these lines of text, which is a great explanation of border parameter of a convolution layer. So run the cell, and now we have add 2 convolution layers in our model. One is, this is a first layer, this is a second layer, and then we see what is the dimension of our feature matrix when we convolution with the 2 layers, 2 filters, 1 and 2. It's mean after 2 convolution layers, what is the dimension of our feature matrix, which is 4, 4, 1. It's mean it's decreased by half. So next we check the effect when we change the size of filter. It's mean the same code here as you already see in the above cells, and then create a model, and then we add a convolution layer in the model, but at that time we increase the size of kernel matrix. It means it's now we operate convolution operation with input image by a 5 cross 5 kernel matrix, 5 by 5 or 5 cross 5. So we check the model summary, run first and then run this. So it's mean if we increase the size of kernel matrix or dimension of kernel matrix, and then the shape of input or dimension of input matrix will be reduced. With padding, now we discuss the padding parameter of the convolution layer. So run the cell. Now we padding parameter set the same. It's mean there is no affect the dimension of output features. Run the cell. When we set same, so run the cell. Okay, after first layer the feature matrix dimension is same, and after the second convolution layer also the dimension is same, and also the third convolution layer the feature matrix, the shape of feature matrix will be remain unchanged or same. So this is the effect of padding parameter on the feature matrix. Next, downsample input with stride. Hope you study these lines of text which are actually explaining the how we downsample the dimension of a feature matrix. We also run this code. We have a data. Run this. We set the parameter stride 2 by 2. So we run. So when we set the parameter stride 2 by 2, the output features is the dimension of output feature is reduced even 3 by 3. So define vertical lines, set the models, and then check the output matrix. You can see that our input matrix, when we use the stride pattern, stride and the value of stride is equal to in convolution neural network, in convolution layer, then the size of output feature is 3 by 3. So this is the whole concept of parameter of convolution layers. I expect you understand well, and please read carefully this lecture, and thank you very much. See you in the next lecture.